Hey everyone, welcome to our talk today on generative AI model pre-training on Kubernetes. By way of introductions, my name is Anish Asthana. I'm an engineering manager at Red Hat in the OpenShift AI group. I've been working on cloud-native AI for the last 7 years or so now. My co-speaker's name is Mohammad Nassar. He's been at IBM Research as a research scientist for the last 4 years or so, working on data engineering and hybrid cloud technologies. Unfortunately, he was not able to make it to Denver for the conference, so I'll do my best to represent him. So, a quick overview of the agenda. First up, we'll be talking a little bit about what data processing workflows look like for training and tuning. Then, we'll talk about scalability and productization concerns, followed by a quick demo, and then an introduction to another open source project to simplify constructing these pipelines. Let's talk about data processing workflows. First off, you have the data corpus, right? You can't do data engineering without data. In our case, the data was stored as Parquet files in arrow table format, pretty standard stuff. When dealing with large data sets, duplication or semi-duplication is almost always present. As such, the first step in the process is usually some combination of exact and fuzzy deduplication. The next step may involve things like natural language identification and filtering. This will allow you to do language-specific processes in follow-on steps. After that, depending on the source of the input data, you may have several annotative transforms that you need to do. An example of that would be identifying if the data has personal identifiable information in it or not. Another one could be checking for the presence of hate, profanity, or abuse language. Once all of these transforms are done, you'll then go on with filtering and finally tokenization. All of the annotative transforms I just mentioned are embarrassingly parallel. What that means is that each one of these is adding data into a separate column of your arrow table. As a result, you can execute them in any order you want or in parallel. If you're doing it in parallel, all you need to do is just merge the output data into one thing at the end. Another form of parallelism we often used was based on language. Once you've identified and split your data based on the language, you can perform all the same data preprocessing for each one of these languages in parallel. They do not depend on each other. Now that we've talked about the high-level workflow, let's talk about the first challenge, which is scalability. How do we make sure that our local development experience is quick and easy, while being able to scale up to production environments in a way that makes sense? In our case, the answer for that was with Ray. Most of our processing stages are built on Ray and are able to scale up to tens of terabytes of text documents across different domains and languages. To attempt to describe Ray in a single sentence, it is an open source framework that provides a distributed compute engine with different primitives for building scalable machine learning or data processing or any sort of workflows without needing a lot of distributed systems experience. The barrier to entry is not that high. Obviously, it helps to understand what you're doing. Our developers really appreciated how easy it was to go from local environments and local development up to our large Kubernetes environments. So how do we bring Ray to Kubernetes? Well, we did that using the KubeRay operator. This operator brings core Ray objects, such as Ray jobs, Ray clusters, and Ray services to Kubernetes. As it's an operator, it means we get to use our favorite things. You guessed it, YAML custom resources. While I love YAML, most of our users actually hated it for some reason, so we had to find a workaround for them. We did this using the KubeRay API server, which allowed our users to make normal, simple API requests that were then translated into YAML custom resources, which the operator managed. This isn't a deep Ray talk. I think there's a keynote on Ray tomorrow as well, so definitely check that out. Now, to talk about some of our usage of Ray, All of our array-based data transformations were based on the driver-worker paradigm. The driver would be reading the input files or object names and dispatching them to our workers, which would then act upon them. Unlike Spark, Ray does not use partitions, or we were not creating partitions. Instead, whenever a worker was finished processing a file, it would request the driver for the next workload. With our data sets, we found that a lot of our files had very different file sizes, so this helped prevent slowdowns with unnecessary waiting. Another thing we did was that each worker is writing and reading from S3 independently. This allowed us to spread the network workload across all the workers, Kubernetes pods, and nodes, thus fully using our hardware. We also use separate array clusters for different data processing tasks. So each time we need to do a different type of annotative transform, we'd spin up a new array cluster. This allowed us to have task-specific images. So the odds of dependency conflicts went down, and if you wanted to build specialized images for whatever reason or use case, we could easily do that. You may think that this adds overhead, right? We're spinning up a new array cluster per task that we're doing, but that was actually okay in our case because each data processing task would go on for so long that the startup time, we didn't really care about it. What else? Okay. Last off, we also had to implement a checkpoint and recovery system. These tasks were running for a long period of time at a very large scale, so you need to have backups in place. You need to have a way to restart from a checkpoint if something goes wrong. So we've scaled up to these clusters, but now the next thing we were running into was running our experiments in a reproducible manner. We did that using the Kubeflow Pipelines project. Kubeflow Pipelines is built for orchestrating jobs of any sort, really. It doesn't really matter if it's going to be a long-running job, a short-running job, what you're trying to do with that job, or even the environment. You can run on Kubernetes. That's what we did. Some people like running things locally. There's three main ways to write Kubeflow components. Components you can think of as steps. Different levels of complexity. You can have very basic Python components, which are based using just normal decorators, or you can write very complicated, fully custom containerized components. So if you have some very specific Java code that you need to run that interacts with Spark in some weird way, you can do that. Next, I just want to show off the UI, because I think that's one of the main selling points of Kubeflow pipelines. You can see all the pods running, executing. You can view logs. You can see how the steps are related to each other, inputs, outputs, events. This makes it very easy for you to monitor your jobs as they're running. Great for the operators. So we talked a little bit about SDKs. Not everyone likes SDKs, especially when you're being convinced to use a new tool. For that, we have something called the Elira project. Elira introduces a drag-and-drop interface that you can use to create your pipelines from Python files. Now, it's not as flexible as using the SDK, obviously, but it's a very great starting point. So if you're not sure about KFP, check this out. So to summarize some of the key benefits we saw from using Kubeflow pipelines here, the first one was modularity. Our workflows were broken down into reusable shared components, making it easy to build and debug pipelines by chaining together smaller individual tasks. Since these tasks were reusable, we didn't have to stress too much about, am I doing things the right way? Next up, KFP also maintains a history of the executions. What this does is it makes all of our experiments fully replicable. So if I ran a pipeline 3 months ago, I know what input parameters it was run with, what the outputs were, and if I wanted to run it again, I can do that easily. Last up, I touched upon this, visualization. The UI makes it very easy for you to monitor your pipeline runs, view your experiments over time, and troubleshoot issues without needing to go into your command line or understand Kubernetes. This was a godsend for most of our data scientists who hated using Kubernetes. As a result of all of these, once they're done with their initial explorations, data scientists are no longer involved in the picture. They can continue to focus on the things they care about, future investigative work, whatever they want to do. And our operators who understand Kubernetes can do what they're good at, which is running these pipelines and making sure they keep working. Let's see if this works. So for my co-speaker, we have recorded his portion ahead of time.
Hello everyone, thanks Anish. So now let's show how we implemented each step of data processing using Kubeflow and Ray as a single step pipeline while utilizing the benefits of KFP as Anish just showed, like modularity and reusability. So the first subcomponent of the pipeline will be argument preparation or computing some input parameters that need to be computed in runtime rather than in compilation time. The next subcomponent is deploying or creating the Ray cluster with the required configurations. Once the cluster is ready and running, KFP can execute the job or submit the job to it. And the last subcomponent will be destroying or deleting or cleaning the Ray cluster. This step is important and should be run always, regardless the result of the execution succeeded or failed, because we always want to clean all the environment. This is done by using exit handler in KFP, which is similar to try it finally in the programming languages. So all the three components here, deploy, execute, destroy, or start, submit, clean, they are implemented as shared component and remain the same across all the standard single step pipelines. Okay, here we can see an example of KFP run of a single step pipeline. As we see here, the four steps that we showed: first, compute and prepare parameters, start Ray cluster, execute, and stop Ray cluster. Each component is created using YAML definition that can be loaded in Python. Okay, so what we saw until now is a single step pipeline that implements a single data processing step. However, what we need or what we aim to do is to automate multiple steps or even the whole workflow that we saw in the beginning of the talk. To do so, we use KFP to create multi-step pipelines that build from multiple components of single-step pipelines as nested pipelines. Each subcomponent here is the component that we saw in the previous slide. The feature of nested pipelines was introduced only in KFP v2. So in KFP v1, we use a workaround using the KFP client SDK to execute predefined pipelines from inside the multiple or the multi-step pipeline. Here, for example, we can have deduplication as the first step, then language ID in the second step, and filtering in the third step, and so on for the next steps. Okay, so now let's move to the demo that shows an example of data processing workflow and how it is done with Ray and KFP v1 and v2. So let's start with KFP v1. We can see here list of pipelines uploaded to the KFP. The first one is the multi-step pipeline, which is the data workflow we want to run. Let's show it. Here we can see the definition of the flow of the pipeline, starting with document identification, then exact deduplication, then we have language separation and filtering. After that, the step of quality annotations. These are running in parallel in sub-pipelines for the three options of English, Japanese, and French. The rest of the pipelines are single-step pipelines that are used in the multi-step. For example, the doc quality, here we can see the four sub-components that we showed of compute, start, execute, and exit. Let's launch a run of the multi-step pipeline. You can press create run. There is a list of input parameters, but don't be stressed. Most of them can keep as default or as a copy of a previous run. Okay, we can start the run. We can see the run we just created in the run tab with the status running. Then we will see a new run of doc ID that was launched by the multi-step pipeline. We can check the progress of each run. We can hear doc ID is completed and the deduplication is started. Then the next step of language ID will start. We can check the editor progress and completion and check all the logs and the pod of this step. We can do this the same for all step and sub-steps. This is just for example. After that, continue the rest of the flow with language ID running in parallel, then the doc quality for each language. We can see all the multi-step pipeline completed with all the subcomponents here. Now let's move to the KFP v2 and see how the workflow is running there. So here in KFP v2, it's more like real nested pipelines where we can enter each subcomponent as sub-pipeline. We can launch the run here, the same thing, list of parameters, then we can press start. Then we can monitor the progress of this run. Here in KFP v2, it's only one run that has all the work, unlike the KFP v1. Okay, we wait until the run is completed. Okay, now let's check now the result. We used min.io for input and output storage. The input is a Parquet file with some documents in different languages. In the output, we can see a separate folder for each language. Here, for example, we can find the output Parquet file with metadata and logs and so on. Nice. So this work of KFP with Ray is used by the IBM team to train Granite models. Here is one of the examples of jobs executed in production. It is fuzzy deduplication task with input data of about 8.5 billion documents with compressed size of 23 terabytes. In the output, we got something like 5.6 billion documents with size 14 terabytes. But the interesting part is the Ray cluster configuration, which had 7500 CPU cores and 56 terabytes of RAM, and it took almost 40 hours to finish. Okay, so let's now move to the third challenge that we will talk about, which is inconsistency. The problem that data scientists or developers can face when working with data processing that each one or each team implements a different data processing step independently. And we can get to a situation where each data processing step is implemented in a different way, with different structure or different input outputs or different programming language and so on. This situation can create a big challenge. For example, for newcomers that want to create a new processing step, so they have a big overhead or have to do duplicated work, also make the maintenance harder and many other problems. So, in order to resolve this challenge, we introduced an open source project called Data Prep Kit, or DPK. DPK is a framework designed to provide a consistent way to implement data processing tasks. DPK has pre-built modules and tasks that everyone can use, like accessing S3 storage, generating metadata, and many others. Also, DPK provides abstract implementation of Ray and Spark, so developers can scale their tasks without overhead, and their code can run on laptops to Ray or Spark runtimes. In addition, DPK is fully automated with Kubeflow pipelines. DPK was extensively used by IBM Granite for training the Granite LLM models, and it recently became part of LF AI and Data Foundation. This picture is from our DPK paper, which was published at the Big Data Conference last year. It demonstrates various DPK transforms or operators built on top of shared libraries and different and variant runtimes. DPK can be used not only for model tuning and data preparation, but also for RAG and other data processing scenarios. We encourage you to check it out. Here we provide a QR code linking to the project, the open source page, and QR code for the KFP community. Thanks all for listening. Anish?
1 second, let me get to the right slide. That is it actually for most of the talk. So let's put that in. All right. So hopefully you've seen that you can use some OSS components to do data processing at scale, right? Granite foundation models, this is the largest scale, or one of the largest scales you can operate at. So, Kubeflow, KubeRay, Data Prep Kit, Kubernetes, this can all work for your data processing needs. Here's some QR codes, one for Data Prep Kit, one for Kubeflow. But if you have any questions, I'm happy to take them now. So the question was, how does this compare to Apache Airflow? So in this case, I guess we'd be talking about Kubeflow pipelines. They're very comparable, right? So the workflow engine's a workflow engine. In the case of Kubeflow pipelines, we actually use Argo under the hood as our backing workflow engine. What we liked about Kubeflow pipelines when we started the project and we've developed it is the UI is more purpose-built for data scientists. From a functionality perspective, not that different.
I was kind of curious, you mentioned Kubernetes and Ray. Is it possible to have jobs that have specific hardware dependencies like Kubernetes and so on?
Okay, so the question was, is it possible to have jobs that have specific hardware dependencies? And yes. With your array clusters, you can specify the types of tails toleration, like you can specify the nodes that your job needs. It's Kubernetes YAML. You can specify the hardware requirements. And then from the node perspective, you just put taints on them so that your jobs get there. So you don't want to run your web server on a node with expensive GPUs. So yes. I think I saw a hand somewhere else. Okay, cool. Well, I'll be hanging out outside, so thank you all for coming today.